So this is the plane, and then let me draw. Okay, so in these orientations, we have the principal stress is 2, and in that direction is 12. In this is 10, right? The 10 is still aligned to x1 direction. So this is the x1 directions. This is in x2 prime direction. This is in x3 prime direction, right? Are we okay?
What about the
And not done yet, not done yet. So for this one, this is the principal stresses in principal directions. Okay, so this one, the m vector for this one is 1, 0, 0. In terms of our original coordinate system, the m vector will be 0. Cosine 26.5 will be approximate. Okay, let me just write it. Okay, and then you can write it up, the n for this one as well. Okay. So that is the principal directions. And now we can, based upon these principal directions, let me redraw the elements in good way. So let me redraw this one here. x1, and this is x2 prime, x3 prime directions. And the distribution, the magnitude, this is 10, this is 2, and this is 12. Okay. So the same, this is the principal directions, then we can use the little guy projection skills, and we put one person sitting on here, and basically this one is corresponding to this figure here already. Are we okay? This person sitting onto in x1 directions, then what he see is this one, 2, 12, 2, 12, right? And this one corresponding is this curve, this figure we already draw. And then in x2 prime directions, so that means here we move the little guy to sitting here, looking into here. And that one, what he see is which one? 10 and 12. For this one, let me superimpose into here. So for this case, you can see the center is at 11. The radius equal to how much? 10 minus 12 minus 10 divided by 2 plus 0 squared equal to 1. So for this case, center at, yes, 11. Is that right? Let me double check.
So you're not going to have any shear forces on that new diagram since you moved different directions?
Yeah. So let me get rid of those unnecessary remarks. Okay. Okay. So that circle corresponding is here. This is 10. Using green one. Okay. And the center here is 11. So here is 11. And here is 10. Okay, now the third one is we have the third guy using the sitting onto the x3 axis looking downward. So that means in the x3 prime directions. So what he's seeing is 10 and 2. So for this case, you can see the center is at 2 plus 10 divided by 2 equal to 6. The radius equal to 10 minus 2 divided by 2 square plus 0 square is equal to how much? 4. Okay. So that is so this position is 6 and using 4. So that is from here to here is 4, from here to here is 4. So the 3 circles basically tangent to each other's.
Hey, didn't you do this once? Not here. Last semester.
Yes.
What was that for?
That is for principal stresses in 3D, in 3-dimensional. And in the last semesters, if you've taken the sections from me, then in the last semester we directly starting from here, starting from the principal orientations. But here we get one step up further, and we start from at least we know one, then we can do that one here.
Okay. So I was like, this looks.
And then back to Sarah's question, she always have a question to me. And
Keep you on your toes.
yes.
That was so bitter.
So what was the question? The maximum shear stress, right?
Mm-hmm.
So the maximum shear stress basically determined is by you look at the maximum circle. The radius of that maximum, the biggest circle give us is the maximum. Whatever the direction you're looking into, that is the absolutely maximum shear stress you will get for this question, for the 3D. And for this case, that would be the corresponding to the black one. The black one is how much?
5.
The radius 5. That happened where? That happened corresponding to the x1. The black one corresponding to this viewpoint. So that means in this way, again, here is more important. So the maximum shear stress you must be obtained by doing this, rotating about the x1 axis in certain degrees, and that is in, so basically the maximum principal stresses could be in the plane. That means if you rotate about the x1 axis, then that plane basically is could be something like this one. Okay. Okay, so that means here we are not only able to identify the magnitude of the maximum shear stress, but also we will be able to identify in drawing which plane in which the maximum shear stress would occur.
Wait, can you say that again?
I'm saying yes, we can do it.
Okay. But this is a nice problem. You gave us a lot of zeros, right?
That is on the homework. And here a lot of zero, because here again for the method, for the second method, we must know at first is starting from one principal direction. If we don't have any starting point, if we start with anything without any principal direction, then sorry, you go forward with this method one, and just do it. This is kind of brutal force, you will get it, but it has less physical intuition about the direction or orientations.
So, just overall, though, when you won't have some extra stress at this point, right? You shouldn't. The stress should be. I mean, like the shearing stress should be zero at this point, right?
Because
Yeah.
this is the principal direction.
Yeah.
Yeah.
Okay. And then for the. So then that end right there by your hand, then that's the new one? That's the new direction?
That's in this direction.
That's the other principal direction.
Yeah, so this is this. And right now for this one, I simply just rotate it into the right angles we see.
So if I'm like looking for my maximum shear stress, when I get to the maximum shear stress, does that make my sigma constantly at 7?
Sigma constantly at 7, what I mean?
If your normal stress, or if your maximum shearing stress, the line can be straight up and down. Does that mean your sigma is going to be 7 on both sides?
Yes, yes.
So like if you like designing
Let
something.
me draw this one here. So at this point, or this point corresponding into the representation, that is 7, 7, 7, 7, and that is 5. Yes, like this one.
So like if I'm designing something and I have more constraints on my shearing stress, then it's probably
Not only shear stress, but also normal stress will be there as well. Yeah. Chris.
The eigenvalue function where you get sigma 1, 2, and 3, is that going to give you the 10, 2, 12?
Yes.
Okay.
If you're going to solve for that one, basically this number will be, for example, 10 to 12.
Oh, so that's what that means?
Yes. Yeah, and then this one, 10 corresponding, my goodness, and 1, 0, 0. Okay. And this one corresponding to, for
0,
example,
cosine 26.
yes, yes, correctly. So here, I think that is what I like to see. So since you are able to gradually kind of grab the numbers with the drawing or directions, yes.
But they're not
Mine.
scaled right on the...
No, this one, of course, in MATLAB, it won't give you the very good numbers, and you have to scale with whatever you obtain. So MATLAB maybe give you a 200 or certain scale number up as something, but the ratio should be keep the same as we did here. Okay. Good. We're good. Good. So these kind of techniques are easier to, I think it's easy to memorize for long term. Okay, so if you really know, and again, I would try is using the method tool because that will give us more intuitive information. But the method tool, again, you have to know if starting from at least you have to identify one principal direction starting from there. If not, then no way. Okay.
If you gave this to us on the test, we would have to use method 2.
Then I will ask Dr. Peterson how he designed his second test, and I will mimic the style.
What? Why? Why are you bringing thermo into this? This is a different subject.
Different subject, yes. Any more questions before I raise? And I want to jump into the transformation of the strain. The strain will be very, very straightforward as long as you know how to do the Mohr circle for stress. Then that is simply one step, and that's it. And even if we've done this one today, we